Hello, this is our presentation for our ME106 final project for spring 2025. For our final project, we chose to do a driving safety system. Our mission statement is that cars are driven everywhere, but human drivers are prone to distraction, causing 400,000 plus injuries and 3,000 plus deaths in 2024 alone. To address this issue, we developed a driving safety system to help avoid accidents by monitoring distance and direction. Sensors continuously gather real-time data, while an integrated program processes this information to issue appropriate commands. Our project aims to enhance road safety and reduce collision risks. This is the Raspberry Pi Pico, which is the heart of our project. The Raspberry Pi Pico is a microcontroller which uses MicroPython that we can use to program the different information and processes that we have between our motors and sensors. By integrating it with the MakerPi Pico, a prototyping board that you can see underneath, our connections are made simpler and our prototyping is made faster. This is an ultrasonic distance sensor, which we use to sense the distance between the front of the vehicle and any obstructions or obstacles on the road. This is an RGB color sensor. We use two of these as brightness sensors. To simulate a road, we use a line of electrical tape on the floor, and we place a color sensor on either side of the electrical tape. Then we can use the brightness values as determined by the color sensors to make smart decisions about how the vehicle should drive to stay on the road. This is a simple DC motor which we use to accelerate the vehicle. This is an L298N dual H bridge, which we use to supply power to the DC motors while preventing the Raspberry Pi Pico from burning out, as the voltage that the motors require is higher than the Pico can handle. This is a microservo motor, which we use to steer the vehicle left and right. Here's our wiring diagram. You can see we use two Raspberry Pi Picos, and this is because the Raspberry Pi Pico only has two I2C connections, while we need three. One is for the ultrasonic sensor, and we need one more for each of the two light sensors. This is our 3D model of the design. You'll notice that the ultrasonic sensors and RGB sensors are mounted securely at the front, while the rest of the electrical components are modeled to be mounted around the rest of the vehicle. This is our final design with and without the cover. I'll now discuss the drive program. To drive correctly, the Raspberry Pi Pico receives distance values from the ultrasonic sensor and then controls the DC motors through the H bridge by using pulse width modulation, or PWM. The Pico checks that if the distance is less than 5 centimeters, then the motors stop, bringing the vehicle to a stop. If the distance is greater than 20 centimeters, then the motors are set to the maximum speed. And if the distance is between 5 and 20 centimeters, then the speed is scaled linearly between 0 and max speed. For the steering program, two RGB sensors supply brightness values for the left and right sides of the electrical tape line. A raw error is calculated by subtracting the two, and noise is filtered out by using a summed weighted average and a constant alpha value between each iteration of the while loop. A dead zone in the middle keeps the steering centered if there is not a large difference between the left and right brightness values. This reduces any jitteriness that there might be from not having a dead zone. When outside the deadband, steering angle is determined by summing the middle angle with filtered angle multiplied by a proportional constant k.